Okay, all set. So we are in module 2, lecture 3, right? Last time we spoke about arc length, right? Do you remember the definition? So if you have a curve parameterized by t, right? What's the definition of the arc length? S of t equals integral 0 to t. Quickly.
Mod of alpha dash of t.
Let's put xc
Epsilon
here.
into d epsilon.
Yeah, because they don't want the same t to appear. Okay, so we looked at some properties. For example, S was monotonically increasing for regular curves, right? That was one. As a result, S as a function of t is invertible, right? So if you can either look at t S as a function of t, or you can look at t as a function of S, right? So this was invertible. And then the other thing we said was, so this was directly as a result, and the speed, right? We talked about the speed of the parameterization. So this was simply ds by dt. How much was this? Mod alpha prime, right? Everybody with me so far?
Yes, sir.
Okay, so like we discussed many times before, there are multiple ways to parameterize the same set of points, right? So if I had one curve, the same set of points could be parameterized in another way. So the reason to bring this up is because, okay, we'll talk about that. So suppose I superimpose a rigid body motion, right? So I'm basically rotating and translating this. What will be the parameterization of this curve? Let's call this set as gamma 1 and this is gamma 2. Both are sets of points, right? Everybody with me? So imagine a beam is undergoing a rigid body motion, rotation r, translation t, capital T. So what is the equation of curve of the rotated beam gamma 2? What is the curve parameterizing that? Any thoughts?
Sir.
So I'm looking for, so gamma 2 is also a curve, right?
Yeah.
So what's the parameterization of gamma 2 over this parameter small t? Anyone else?
Sir, R and T will be applied over alpha, sir. Right, sir. It
Correct.
is like a transformation.
Very good. So give me a way of writing beta of t equal to. So what you do is you come here, you take some point t, right? This is what I want to call beta. So if you apply alpha, you will go here, correct?
Yes, sir.
How will this point x change after applying r and t? What will be y? Rx plus t, correct?
Yes.
So what should I put?
Yes, sir.
So
yes, sir. Yes, sir.
x is equal to alpha of t,
alpha t.
right?
Yeah.
So the parameterization of the rotated curve will just be r alpha of t plus the translation. Everybody agrees? How about Gayan, Aditya?
Yes, sir. Yes.
Does it make sense? So
Yes.
basically you're chaining together, right? You're chaining together. Or you can also say that this is a composition, right? This rigid body motion acts on the result of applying alpha, right? That's why you get R alpha plus T. Now, what
sir,
do you think?
Sir, actually, this reflections also does, we can apply in the same way.
Yeah, we can apply anything. The reason I'm talking about rigid body motion is because of one reason. Reflections also will have that property. Yeah, sure. With the reflection, R will just have some, instead of R, you will have some other transformation, right? Okay. So what do you think will be the length of the curve gamma 2 compared to gamma 1?
Same.
Same. If I took an infinitesimal section here, right? Let's say ds. What do you think its length here will be?
Sir, integral of beta of t dt.
So if I took the length ds here, what will the corresponding length here be? Do I need to compute it or can I make a guess?
Yes.
ds, right? Because you're just doing a rigid body motion. No lengths will change, no angles will change. I mean, angles will change, angles will rotate, but relative angles will not change, right? Okay, so the other question then is, what is the speed of parameterization of the rotated curve? So of gamma 1, we know the speed is ds is mod alpha prime, right? What is the speed of the rotated curve gamma 2?
Beta
Chetna?
prime.
Beta prime.
Beta prime, sir.
Yeah. Can you improve this guess a little bit?
Yes, sir. R into alpha prime.
Correct. No, what I meant was, is there a, so imagine that the speed basically measures how fast, let's say, you're traversing this curve, right? How fast you're traversing these two curves, right?
Yes,
So
yes, sir.
imagine you're sitting in a car that's going around a track, right? So the speed at which you drive basically depends on whether you're at a straight section or a curved section and so on, correct?
Yes, sir.
Okay, so if you just rotate the track a little bit, okay, is your speed along a straight section or a curved section going to change? Okay,
Yes, yes, sir.
maybe imagine a race track like this, right? A race track like this. So you will have one speed here, another speed here because you're going along a curve, another speed here, and another speed here. Agreed?
Yes, sir.
Now I'm applying a rigid body rotation and a translation to this, right? And assume that the driver is consistent, right? So along this section, he or she will go at 1, then here at 2, at speed 3, and at speed 4, right?
Yes, sir.
So when traveling through this point, x, you will be at this point corresponding point y, which is rx plus t. What will be your speed at this point y? The same, right? Same as it was at x.
Yes, sir.
Okay, so I mean, I intuitively feel that this should be the same as alpha prime. What do you think? So when you are passing by this parameter t, your speed here is mod alpha prime of t, right? Your speed after rotation will probably be oriented differently, but will have the same magnitude. What do you think?
Yes.
Yes, sir.
Okay, let's work it out. Okay, what is the tangent? What is the tangent to gamma 1? Right? You would say this is the vector alpha prime of t when you are at point t, correct?
Yes, sir.
Tangent to curve gamma 2 will be beta prime of t, right? So we can get that by differentiating d by dt of r alpha of t plus capital T. Agreed, Chetna?
Yes, sir.
So how much will this simplify to? Is r a function of small t?
No, sir.
And how about the capital T?
No, sir.
No. So we just get r alpha prime of t plus capital T. Agreed?
Yes, sir.
So this tells you that the tangent of gamma 2 is just a rotation and translation of the tangent of gamma 1. Agreed?
Yes, sir.
So tangents are simply rotated, right? And translated. Okay. Now, how about someone else? Gayan, how about the length of beta prime?
So the translation term, if we differentiate, will go to 0, right, sir?
Yeah, correct. I agree. Yeah. Just rotate. I agree. Yeah, mistake.
The beta prime will be same.
Beta prime will be same. Let's do it. So how much is the length of beta prime? R alpha prime dot R alpha prime, correct?
Yes, sir.
Let's do this in index notation. How can I compute this dot product using index notation?
So that would be R transpose into R.
That's one way to do it. So you can write this as alpha prime, R transpose R, alpha prime. How much is this?
This would be identity matrix.
Identity because of rotation, and therefore this will just become alpha prime dot alpha prime equals mod alpha prime square. Agreed?
Yes, sir.
In terms of index notation, how can I write the same, do the same calculation? I mean, just for practice, right?
So we can write Rij into alpha prime j.
Okay, alpha prime j, and then
Rik into alpha prime k.
very good, right? So you're taking the ith component of this and the ith component of this, right?
Yes.
So this we can therefore write as alpha j prime Rij Rik alpha k prime, right? So
Yes, sir.
then you kind of mimic the same calculation here. This is R transpose Ji Rik, correct?
Yes, sir.
This is simply R transpose R's jkth component. Agreed?
Yes, sir.
And this is therefore delta jk. And so you get alpha j prime, alpha k prime, delta jk, correct? So this is simply alpha j prime, right? So that is why you get alpha prime dot alpha prime. Okay. So you see that the speed does not change with rigid body rotations, right? So that automatically tells you that the arc length of gamma 2, which will just be beta prime, right? This remains unchanged from gamma 1, right? So this is basically a way of saying that arc lengths are preserved by rigid body motions. Makes sense, right? Everybody with me so far?
Yes, sir.
Yes, sir.
Okay. Then the next thing I wanted to talk about, let's do an example. Let's do a couple of examples for computing arc lengths. Okay, so let's do example 1. Let's take a circle. Theta gets mapped to r cos theta and sine theta, right? How do I find s as a function of theta? Do you remember the answer? What should this be? Aditya?
So,
What is the arc length? You speak by angle theta.
theta by 2 pi into 2 pi r.
R theta, right?
R theta. Yes.
So we should get back this, right? So let's reproduce this, right? This is a known answer. Let's reproduce this. What is the function alpha in this case? Go ahead, Aditya.
Arc. Okay.
Correct?
Yes, sir.
How much is alpha prime of theta?
Minus r sin theta, r cos theta.
Very good. What is the length?
R.
Very good. So S of theta will be integral 0 to theta mod alpha prime of t dt, right? So this will give us r theta. Agreed? Because this is a constant.
Yes, sir.
Okay, very good. Let's do another example. This is a little bit more involved, but I'll use this for more explanations. Okay, so take this curve. This is the polar curve. R of theta equals a e raised to b theta. Okay, you can assume that minus infinity less than theta naught. So this is basically a spiral. It will keep going out. Okay, so I've specified a curve in this form. I'm saying that this is a polar curve. What does this mean? This is the angle. This is the parameter theta. Correct? So Naresh, do you want to take a guess about what will be the map alpha in this case? See here. Yeah, go ahead, Naresh. I can't hear you though. Maybe you're having some trouble with the mic. Okay, Gayan.
Sir, I'm not able to get that part, so I can't explain properly.
But okay, what do you think this means? R of theta equals
Yes.
some number. What do you think it means? Why do you think we put an R here?
Sir, actually it is in the polar form, na? So R is varying with respect to theta. As theta is varying, R is varying. So that's
Polar
why we are.
coordinates. Very good. In polar coordinates, how do you specify the coordinates of a point?
So on the basis
You
of R, it is a function of R and theta.
Very good. So if I gave you the radius and the angle, how will you write the x and the y coordinates?
So x is equals to R cos theta and R sin theta.
Y is equal to r sine theta, right? Exactly the same thing is happening here. So what this
Yes.
is saying is, if you go along this parameter range, right? If you go to a particular theta, the radius of the point on the curve is given by r of theta.
Okay, we are straightening the curve. Okay.
Not straightening, we are winding.
Winding,
Right? So
winding,
it's
winding.
saying that. So if you wanted to plot a point on the curve, right? If you want to plot a point on the curve, you say, okay, I want to plot a point at angle pi by 4, right? Then you have to put in pi by 4, and this will tell you what radius at which to plot at. So this will be the point. This will be r of theta. Make sense?
Okay, sir.
No, so what is alpha? Alpha of t equals
Alpha of t equals.
theta is the same as t, okay? Just choosing a parameter. Same thing, apply the same thing. So
R
the
cos
x
t is x
coordinate would be r of t cos t,
cos t. Okay. So cos
r
t
of
or cos theta?
cos t, correct, cos t.
Cos
And
t.
this will be r of t sin t, right?
Yes.
So if you write it out with the particular expression given here, you'll get alpha of t is a e power bt cos t sin t. Okay?
Yes, sir. Yes, sir.
Okay, so what is the tangent alpha prime? This will be a b e power bt cos t sin t plus a e power bt minus sin t cos t. Agreed?
Yes, sir.
Okay, so let's factor out. So you can factor out a e raised to bt, and so you'll have minus sin t plus b cos t, and here you will have cos t plus b sin t. Everybody with me? Okay.
Yes.
This means that if you are at some point t in parameter space, the tangent has to be sketched at this angle. The vector, the tangent vector will be parallel to this vector, right? So what is the length of alpha prime? This will be a e raised to bt times the norm of whatever is inside, right? Okay, so this will give us sine square t plus b square cos square t plus cos square t plus b square sine square t, and then you'll get a plus 2b sine cos minus 2b sine cos. Agreed? Because of a negative sign and a positive sign here. Everybody with me? Okay, anyway, this is just algebra. So this will give us a e raised to bt root of 1 plus b square, right? Do you agree,
Yes.
Gayan? Okay, so
Yes,
what
sir.
will
Yes,
be
sir.
the arc length? S of t will be integral 0 to t a e raised to bt root of 1 plus b square. Let's put xe here, dxe, right? So a and root of 1 plus b square are constants. What is the integral of e power bx? Integral e power bx dx. How much is it?
E raised to bx by b.
Okay. So, Gayan, are you an MTech student or a research student?
Sir, I'm tech student.
Then you should crack this like the gate
Yes.
preparation you did,
Yes, sir.
right?
Yes.
Okay.
Sir, I was thought you were talking to someone else. That's why I just unmuted.
Okay.
Okay. Okay.
Fine. No problem. So you'll get a e raised to bxe by b with xe evaluated between 0 and t, right? So we will get here a root of 1 plus b square divided by b times e power bt minus 1, right? So this minus 1 I'm going to leave out just by absorbing it into some constant. Basically to say what is the starting, this is basically the starting datum level. So ignore the constant, right? So I'm just going to ignore. That's fine, right? It doesn't make any difference. Okay, so we have s as a function of t to be a by b root of 1 plus b square e raised to bt. Okay, so how do you think this function looks? S as a function of t. Guy, this time I'm talking to you.
Sir, yes, sir. I'm trying to get it.
uh, how do you
So
think this?
the starting term is itself a constant, and
So anyway,
so
t
so it
equal to
is
0.
epsilon. Uh,
Then
Sir, at t equal to 0, the function will be 1, okay, and then it will be go exponentially. For example, e has some value of 2 point something now. So if we are increasing the value of t, so up to certain level, there will be a increasing slope.
it will grow, right?
It
So
will
this
grow. Yes, sir.
agrees with what we discussed before, that the arc length, I mean, I'm assuming, of course, that b is greater than 0, right? That the arc length keeps increasing with parameter t, right? Then, again, don't unmute Guy. One last question. I said that s as a function of t is invertible, right?
Yes, sir.
So now I want to write t as a function of s, right? That means previously I was giving you a value of t and I was able to read out a value of s. But now I want to go the other way. I want to give you a value of s and find out what's the parameter t. That means I'm telling you how far I have walked on the curve, and you have to tell me where you are in parameter space, right?
Right, sir.
So how can we do this from this expression? I want to write t as a function of s.
As a function of s. But t.
Again, go back to get mode.
Yes, sir. Yes, sir. Yes, sir. S of t, the t of s translate करना है आपको.
Correct. So you write s equals a by b root of 1 plus b square e raised to bt. Anyone? What shall we do?
Take log.
So you do bs by a root of 1 plus b square equals e raised to bt, right? So you take the logarithm on both sides. So you get log of bs by a root of 1 plus b square. And what will be on the right hand side? bt, correct?
bt.
So you divide both sides by b and you will get this. So this means t as a function of s equals 1 by b log of bs by a root of 1 plus b square. Agreed?
Yes, sir.
Okay, how will this curve look like if I now wanted to plot t as a function of s? How will this curve look like? Should it be increasing, decreasing? What do you think will happen?
So take the reflection of the above curve with x equal to y line.
So you basically have to rotate this plot, right? But do you think it'll be increasing, decreasing, or can't really say?
It will be increasing only.
Why?
Sir, because log x is increasing function.
True. See, the other point, I mean, the reason you already know it's increasing is because there is a one-to-one relation between t and s, right? Because when you say that s is the monotonic function of t, increasing function of t, means there is a one-to-one relation, right? So if s increases, t has to increase, right? So at t equal to 0, we are already at some s naught, and so this will look like some curve like this, right? So then, like you said, this will just be a rotation of, I mean, you have to flip the axis around, okay? Everybody understood? Followed the example?
Sir.
Yeah. Go ahead. Was there a question?
No,
Okay.
sir.
Okay. So the reason I did this example is because because of this fact, a regular curve can always be reparameterized by arc length. What do you think this means? We will use this extensively. What do you think this means? So I've given you one curve, okay? And that means I've specified the range of parameter t and I've given you a mapping alpha, right? So this is the curve gamma. So what do you think this statement means?
T can be S.
T can be true. T can be S. It can also not be S. That is true. But this talks about some reparameterizing, right? What do you want to say about that?
It can always be expressed in terms of S also, if it is a regular curve.
Let's draw an S range also. Let's say the length of this goes from 0 to L. The range of T goes from 0 to 1. Okay. So will the range of S be 0 to 1 or 0 to L?
0 to L.
0 to L. Okay, very good. So if I'm given the mapping alpha, what is this statement saying? We're close.
There is some mapping alpha cap, which
Let's
also
put
maps to the. Okay.
So it's saying that given this curve gamma, you can always express the same curve as a function of arc length, right? So the speed here need not be 1, but the speed here is necessarily 1, right? That means if you walk a distance of 1 mile here, you will walk a distance of 1 mile here. If you walk a distance of one unit here, you may or may not walk 1 unit here, right? So it's saying that if given any plane curve which is regular, that means the derivative doesn't vanish, mod alpha prime does not become 0, then you can for all practical purposes, you can re-express this parameterization in terms of arc length. Okay, so what do you think is the relation between beta and alpha? Alpha is given, right? This is given. Is beta known?
Yes, sir.
I mean, we have to find out, but at this point we don't know, right? At this point we don't know. Okay, so is there a standard way to find what beta is? The picture kind of suggests
Alpha inverse.
Alpha inverse. Okay. You have to be a little careful here. Okay. So you're saying beta is alpha inverse. Which way will alpha inverse go? It will go from where to where? Aditya.
Sir, gamma is alpha of t.
So alpha inverse will go like this, right?
Oh yeah, okay, correct.
Okay.
Alpha composition inverse of S.
Okay, so the point is the following, okay? The way to think about this, one simple way. Suppose you took some arbitrary point T here, okay? Where will this get mapped to? Alpha of T.
Alpha T.
Okay, so at this corresponding alpha of T, okay, so let's say that you have, this is at a distance of S, right? The arc length of this point for this point is S. Okay, so you should have beta of S equal to alpha of T, correct? The point at a distance S has to be the same one. That is just saying that whether you reach this point from the t-axis or from the x-axis, the identity has to be the same, right? It's the same point.
Yes, sir.
Correct? Let me write it more explicitly. Beta of S of t should be alpha of t. If you take a point, if you take a point t, okay, it will map you to a point alpha of t. This point is at a distance s of t, right, along the curve. So beta should be such that beta of s of t should get you to the same point, right? Whether you reach this point starting from the t-axis with alpha or from the s-axis, this is s of t, right? Or from the s-axis with beta, you have to reach the same point. Are you following?
Yes, sir.
Okay. Who is, if you're not, just raise your hand, I'll discuss more. Or one of you say, yes, I understood. I'll proceed.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the thing is that you can start from the t-axis and reach that point, or you start from a corresponding point on the x-axis and reach the same point. The corresponding point is indicated through s of t, right? Another way of writing this is if you start from the s-axis, that means if I go to the point beta of s, right? How can I write this as what will be the corresponding point here? If I start with at a point S, what will be the corresponding point here? Capital T of S. Agreed?
Yes, sir.
These two are identical statements. This is saying that if you start from the t-axis, you will reach the point alpha of t. You can also reach it by going to the corresponding point on the x-axis and mapping it with beta. Or if you start from the s-axis, you map it with beta, you will reach beta of s. Or you go to the corresponding point on the t-axis, which will be capital T of s, right? That is the inverse, and map it with alpha, right? Okay, so the missing link is basically this thing. This is the map capital T of S. You see that there is one arrow this way, one arrow this way, and another arrow this way. So what does this tell us about beta? How should the mapping beta be? Beta goes from S, which is belongs to the interval 0L, and it will go to the same curve gamma, right? And the relation between beta and alpha is that beta of S equals alpha of capital T of S. Okay. What do we get to choose here, S or T? S is arbitrary, right? We can go however far we want along the S axis. How do we get, is this mapping T known or unknown?
Unknown.
Unknown. If you are given the mapping alpha, right? If you're given the mapping alpha, can you construct this S as a function of T?
Yes, sir.
Yes.
Yes, sir.
Can you invert it?
Yes, sir.
Yes.
So
Yes,
is the
sir.
mapping T known or unknown?
It's no.
Known.
Known.
Right? So the previous example gave you a specific case in which you can work this out by hand, right? Okay, so if once you are given the map alpha, S as a function of T is known, and its inverse T as a function of S is known. Therefore, so to go from S to beta of S, you first go from S to T, and then from T using alpha to alpha of T. Okay, so that's what this composition is representing. You choose a point S, you hop on to the t-axis, and then apply alpha to go to the curve. Everybody with me?
Yes, sir.
So both alpha and beta have the same trace, right? That means that they represent, if you apply the mapping beta to S and alpha to T, you will trace the same set of points. You're going to get the same arc, right? But they are different mappings, right? So in that sense, this is a reparameterization. Okay. Okay, so we claim that beta is a reparameterization. It makes sense, right? Now, we say that this is a parameterization by arc length. What do I have to check for beta? So I claim that beta equals alpha composed with T is an arc length parameterization. So what do I need to check?
Beta dash has to be greater than 0.
Beta dash has to be exactly 1. That's what it means to parameterize by arc length. If I walk a distance S here, I should walk a distance S here. Right? That will happen for any arbitrary S, right? That will happen only if the speed of the parameterization is 1. Is mod alpha prime 1?
No, sir.
No, not in general, right? So this could be larger than 1, smaller than 1. The only thing we know is that mod alpha prime is always greater than 0. Why?
Curve is regular.
Regular, because of the regular assumption. So, alpha is not a parameterization by arc length, but we claim that beta defined this way is a parameterization by arc length. So, shall we compute it? So, what is the meaning of beta prime? Should I differentiate with respect to t or s?
S. S.
D by ds of beta of s, correct? So this will be equal to d by ds of alpha of t of s, correct? Okay, how do I proceed?
Sir, alpha prime.
So this will be, let's write in terms of d by d. What should I put here? Alpha?
Yes, sir. Alpha.
Denominator?
Plus. Yes.
S.
T. Sorry. T.
T.
Into.
So you evaluate this at t of s multiplied by
dt by ds.
Okay. What is this rule called?
Chain rule.
Chain. Okay. Everybody followed what's happening here? So how much is this? Alpha prime of t of s, right? Okay, this means you evaluate the derivative of alpha at the point t of s, right? So remember, anything that alpha eats should be in the t-axis, right? You can never evaluate alpha prime at s. Whatever you feed into, imagine, for example, that the units in this t is seconds and the unit in this s is meters, right? You can never feed alpha a variable that has unit of length. You should feed it unit of time, right? So in the same way here, anything that goes inside alpha prime, whatever, should have a t, not an s variable, right? So that's just a check. Okay, so this is alpha prime. How shall we compute dt by ds? Is this known or unknown?
Known, sir.
No, because we know t of s, right? We just have to differentiate this. Okay, all right. But we want to show that beta prime has magnitude 1, right? So we have to compute this. What do you think this will be?
That is 1 by ds by dt.
Okay, so this will just be 1 over ds by dt. Agreed?
Yes, sir.
Evaluated at what t? Okay, let's make sure all of us understand. Okay, so how do you compute dt of s by ds? Right, that's the question. Do you know the map t of s explicitly?
Yes,
Do we
sir.
have an expression? No, do we? I know we can compute it, but do we have an expression for it?
No.
No, right? So we have to do it in some indirect way. So let's do the following. So we will say that s of let's put it like this. So we have to basically say that s of t of s equal to how much? What will this give you?
S.
Does this make sense? You take the arc length s, you get the corresponding t, then you recompute the arc length. You will get back the same arc length. This is just saying that s and t are inverses. So here, this is the variable s. This is the function arc length. This is the inverse function capital T. Can I differentiate both sides with respect to s? Right?
Yes,
I can
sir.
do d by ds of s of t of s. What will be the right hand side?
1.
1. So how do I do this differentiation? Again by chain rule. So I do ds by dt evaluated at T of S times dt by ds, right? This is equal to 1, right? This is exactly what I need. And so this tells me that dt by ds is just 1 over ds by dt evaluated at T of S, right? That's what we used here. Agreed?
Yes, sir.
Okay, so in this way, we now know that d beta by ds equals d alpha by dt evaluated at T of S times 1 by ds by dt evaluated at T of S. Correct?
Yes, sir.
Is this a scalar or a vector relation?
Vector.
Vector, right? So I can take the magnitude on both sides, right?
Yes, sir.
Is this positive or negative or not known?
Positive.
Positive, right? Because S is an increasing function of t. So this will be 1 by ds by dt evaluated at T of S. And then we will have the magnitude of d alpha by dt evaluated at T of S. Correct? What is the magnitude of this vector? This is the length of the tangent at the point capital T of S. How much is that?
Mod alpha prime of T of S.
Exactly. How much is this? Exactly
ds
the
by
same.
dt.
These two are exactly the same, right? And the reason I can cancel them out is because I know neither is 0. Why? Again,
Regular
regular.
curve.
Regular.
Again, regular. Okay, so the takeaway message is that given any regular curve, that means it's differentiable and the derivative never has, the tangent never has 0 length, you can always reparameterize it by arc length. Okay, that means it is enough for us to think about curves which have unit speed. That means it is enough for us to think about curves which are parameterized from 0 to its length. Okay, with some map alpha with mod alpha prime equal to 1. Okay, and in fact, we will use this kind of curve for the center line of a beam starting from the next module. All right. Any questions so far? How about the others who have stayed quiet? Gayan, Chetna, and Aditya, you followed along?
Yes, sir.
Yes, sir.
Yes, sir.
So in homework 2, which I'll post soon, you'll have a chance to exercise some of these calculations. Okay. So it's not, I mean, again, the goal of this description is not to, again, this is not math class, right? I'm not giving you anything that you didn't know already, but I'll stop, we'll pretty much stop the lecture here, but just want to give you an idea of what's coming next. So sorry. So what we will do in module 3, right? In module 3, module 2 is not over. I think I will need one more lecture. In module 3, we will basically consider an inextensible beam. Okay, and we will let it deform according to some loads. Okay, we will deform. What is the unknown? So we know the initial length is 0 to L, right? What will be the length of the deformed beam?
L.
L, right? Not only does the length have to be preserved, the length of every arbitrary section has to be preserved, correct?
Yes, sir.
Yes, sir.
Yes, sir.
So that means, so we will be interested in knowing what is the deformation mapping alpha, right? That's what is the main unknown. How does the center line of a beam deform, right? So if you are considering a beam that is inextensible, this mapping alpha has to be one that is parameterized by arc length. it has to have unit length. Can you explain why? Consider a very small section here, ds. What will its length be in the deformed configuration?
ds.
Yes.
I mean, that's what we want it to be. But if you mapped it with alpha, in terms of alpha, what will be its length?
Alpha ds.
So if this sits at some point S naught, you will have mod alpha prime of S naught ds. Correct?
ds.
How do you know this? Because of the Taylor expansion we did last time. Remember, alpha of S plus delta S equals alpha of S plus alpha prime of S delta S plus higher order terms, right? So this means that the distance between alpha of S plus delta S minus alpha of S equals alpha prime of S delta S, correct? So this is the length in the deformed configuration. This is the length in the reference configuration. How much can this factor be then?
1.
If you want length to be, has to be 1. Okay, that's the reason we are going through all this pain. Okay, so because slender structures can hardly take any compressive load, right? They will immediately buckle. We will look at those problems later on. So it will buckle at some very small load itself, right? So generally they will try to bend rather than compress. Okay, so that's why in many models it is helpful to just think about beams which are inextensible. The cost of changing length is so huge compared to bending, right? It's like saying, do you want to take, let's say it will cost you 100 joules to compress this beam by 1 mm, or it will cost you 1 joule to bend it. Which one would you prefer? Clearly the bending mode, right? Because we are assuming that structures will deform into some energy minimizing configuration. So if it's trying to minimize energy, it's not even going to sample deformations which will cost 100 joules, right? It will try to stay within the 1 joule range. So that's why we will look at deformations of beams which are length preserving, bending dominated. Any changes in length are just so expensive that they are hardly seen in reality also. And occasionally there will be some cases, but generally length preserving deformations or bending dominated deformations are the norm with very thin structures. Okay, so in that case, we know information about the deformation mapping already, right? So we'll say alpha is the unknown, but we'll have a constraint that mod alpha prime should have length 1. Make sense?
Yes, sir.
Okay, so that's why we are going through this material. Okay, let me stop the recording. We'll finish up next time. Okay, finish up.